All right, welcome. Good afternoon. Uh, we're going to do like a little activity to probe what is called as sampling statistics, where if we consider this entire class to be a population, it's a population of 43 students. I'm going to pass a sheet where you're not going to write any name. You're just going to write your height in inches. If you are 5'10" like me, you are 70 inches, just put down that number. If you don't want to write your true height, I don't care. Put a number that's reasonable for a human. Okay. I'm collecting raw data. I need 43 values. I'm going to pass the sheet. Okay. Number one. Number two, this data that I collect is for the entire population. That is the truth. But we are also going to do inferential statistics, or we are going to do inference by breaking up this class into small samples. So I'm going to call, let's say, these 4 students here, they are a sample. I'm going to ask them to calculate their sample, the mean height of that sample and the standard deviation of that sample, while we compile the data and have data on the entire population. So this, how is this is going to work is, can you join them? Can you come here? So 1, 2, 3, 4, 5. You are group 1. And then 4 of you in the second row, you are group 2. So I want you to, one of you, write down all the 4 heights on a sheet of paper or Excel and compute the average and standard deviation and be there. Okay. So this group here, 6, sample size 6, 1, 2, 3, 4, 5, 6. 6 of you together, compute your average and standard deviation. We'll do this 5. Okay. You. From you,
64
5. Okay. 1, 2, 3, 4. 4 of you together. Sample size 4. Okay. And then we'll do another 7. 5 come from 6. Okay. Write down your height in inches, and yeah, you don't have to write.
I did the conversion.
Height and height.
70.
And what you
Okay.
do is
Oh, wait, not over this. Okay. How tall are you? Okay, how tall are you?
So please try to do this with less noise because we have many groups now. For the sample standard deviation, please use the formula n-1. For sample standard deviation, please compute using n-1. The formula is up here. Okay. So who did I call group 1? 5 of you, sample size 5. Who was group 2? 4. Okay, sample size 4. Group 3. 6 of you. Group 3. Okay. Group 4. Who was group 4? 4 of you, right? Group 5. Who is group 5? Five. Okay. Group 5. Group 5 sample size is 5. Who was group 6? Group 6? 7. 7 of you, right? And group 7. Group 7 is last row. 4. Have other discussions later. Let's compute and tell.
Meaning 69.5.
2 decimal points. $69.50. And what is the sample standard deviation?
1.29.
1.29. So you use this 4 minus 1, 3, right? You divide by 3. Yes, no?
Yes.
Okay. So one representative from each group, please call me and tell me your statistics.
66 for 4
You have one more group member coming. So please join this group.
How tall are you? Yeah.
You don't have to.
65, there we go. That's what it's about.
So
Oh,
listen up, please. If you are using Excel, okay, you need to use standard deviation. Okay, standard deviation dot sample dot s. Okay, stdevp dot s. Make sure you use this function and not the dot p, because dot p will have n here. Dot s will have n minus 1. It's very important you use dot s. Okay.
Got 65.8 and then 3.87.
65.8 and 3.87. Okay. Yes. Okay. Okay.
I
1.95. Yeah, thank you. Okay.
Average was 71.83.
71.83.
The standard is, or the deviation is 2.64.
2.64. Thank you.
That was a good average.
Is the sheet going around? Are people writing their height? Pass the sheet. Okay, coming around. Yes. Okay, and what's the standard deviation? Same. What are the odds? Same standard deviation? You kidding me? Okay. Whatever.
What's two more
Is the
decimals?
sheet going around? Are we writing down our height? Yeah.
No, multiple. Let's your goals.
Make it quick, please. Yeah. You are which group? We're group 5, right? Okay. Our mean is 66.8. And 2.28. So only one group is left. Did anybody come after now? Okay, group of 5. Okay, tell me.
Yeah, yeah. That's what it is.
Yeah.
I still gave the variance. 36, our standard deviation is 1.39.
Your group 6, 1.39. So who is group 3? Are you sure you reported standard deviation and not variance? Because this formula is for variance.
You said use Excel stdb.s, right?
Yes. Okay. And group 1, are you sure your standard deviation is 3.87?
If somebody very short.
I see. Okay. All right. So everybody is sure you gave me standard deviation, right? Not the variance. Okay.
Please do the same.
Okay, silence, please. This is not a time to chit chat, please. Let's just get going.
That's it, yeah.
68, right?
It's 68 is the high, but that's easy.
It's not that seems like the sample size.
Okay, silence, please. Where is the sheet? Okay. So this is the data, and what we are going to do now is we are going to look at the sample mean collected based on different sample sizes and ask the question, using this, that is using this sample mean and standard deviation, how do you project for what is the true value of the height for this population? The true value of the height is what? I'll have 37 values written down, and Jonathan is going to compute the average of those 37 values, and that is the truth, which you all won't know, but we will know because he's going to compute it. As an engineer or as somebody who's doing data collection or an experiment, you cannot do an experiment in which you survey or sample the entire population. Most often that is impossible. You agree with me? You cannot access the entire population. It is impractical or too costly or just not possible. So you have to collect a finite sample, and then you have to ask the question, how much can I trust this mean based on a finite sample? So initial thoughts, what would you say is good for data collection? Generally, we say more samples is better, right? But here is how we have some samples which are 6 or 7 and some that are 4 or 5. Okay. Of course, the 7 is better than the 4 in terms of sample size. How should we go about commenting about the true value of this quantity? First question, is this the true value or is this the true value or which is the true value? Can you quickly type this in Excel and tell us? No, don't tell us. Tell me the mean. Which is the true value? Or which value is more reliable? Whose estimate is more reliable? Yours, right? Because it's your group. Mine. No, forget me. I mean, see, you are, if I give you the task, go find out the average height of the people in this class, which we consider like a village or a population. You can't interview all 37. So you chose to randomly interview 4 or 5 people who are sitting next to you, and you came up with a value. Now the question comes to you, how much confidence do you have on this value to represent the true value of the population? Okay. First observation, the sample mean itself is a random number. Right? Every group got a different value, except 2 groups which were conspicuously the same. Maybe they just decided we do once and share the value. Okay, but every group has its own value, which makes the sample mean a random number. Agree? Do you see this? The sample mean is a random number, and it just depends on who you interview that day or what you sample that day, you will get a value. And so is the sample standard deviation. It also follows a pattern which you can't possibly predict because it seems random. Okay, so this sample mean and sample standard deviation, they themselves follow a distribution, and there are some distributions which describe those. Okay, only thing is it becomes mathematically complicated, too complicated for our course, that we are not going to go into the details of those distributions, but I'm going to teach you one parameter called confidence interval. I'm going to teach you a parameter called confidence interval, which is like saying, I have a mean. How confident am I about the mean? It's a parameter that denotes that confidence. When will you be confident of your mean in qualitative terms? When are you most confident? You're able to interview or you're able to sample many trials, and an average got from more trials is better than an average got from fewer trials. So by that measure, this group can be more confident of their answer than any other group because the sample size here happens to be 7. Okay, but it's not just that. Just because you interview more people, does it mean that this estimate is better? The estimate also depends on one more thing. What does this standard deviation represent to you in general, in words? What does the standard deviation tell you? Low standard deviation means what? Large standard deviation means what? Larger range of variation. Like I was kind of amazed at group 1. I asked them, are you sure? And they said we have some really different heights in our group, right? So does that mean the sample mean you get there is unreliable? Does a large standard deviation necessarily mean it's an unreliable data? Why not?
It just means you have a wider range.
It tells you something about the population of the sample, but that doesn't mean your methodology is incorrect, right? It just happens to be a group of 5 people who have different heights. That doesn't mean your methodology is wrong, correct? So it has to be, this confidence interval has to depend on the sample size. What's the correlation there? Larger sample is better. The confidence interval also depends on standard deviation to the extent that a large standard deviation means how should you think about designing your sample? Should you collect more data okay, let me back up. If your standard deviation is small of whatever you're trying to observe versus if it is large, should you plan for more data or less data in which case? In each case, if you have a large standard deviation, do you think collecting more data will help or collecting less data will be helpful? More is almost always the answer. Less is never always the preferred answer. It's like a compulsive thing we do because of lack of resources or time. More data is better, right? So we are going to write down this confidence interval parameter, which I'm going to summarize here. Sampling statistics. Statistics. We're going to talk, we talked about sample mean, sample variance or standard deviation. Okay. And then we are going to talk about confidence interval. We also talked about sample size. Okay. Some notes for me to write down. Sample size, usually a subset of the population. Entire population cannot often be accessed because of complexity, cost, or practicality. Like if you're an astronomer or an astrophysicist and your goal is to get a mass distribution or a distribution of the masses of stars, there are trillions and trillions of stars in the universe. There is no humanly possible way you can count all of them or you can observe all of them. You observe a few and then you make a distribution. That process is what sampling is. And there you are limited by practicality. You don't have enough lifetime to count the number of stars in the universe. That's how many there are. Okay. Sample mean is the value or is the average computed based on the observed trials or samples. Okay. sample mean itself is a random variable that depends on the chosen sample, which is a random process. Jonathan, do we have an example?
Oh, yeah, that's the population meters.
Okay, wait. 68 point. Okay. 3.28. Okay, we'll come back to that. Okay, so this value you must consider as truth. Okay, true value which you can never access in a real measurement scenario. Why? If you're going out there and measuring the temperature of the air, you don't know the true value. Why? By definition, that's what you're seeking. You can't know what you're seeking, right? If you knew it, you wouldn't be seeking it. So this is kind of like a doctored situation where we know the true value and we are going to use it to test our understanding. Okay. All right. Sample. Yes. Was there a question? And then sample standard deviation is the standard deviation computed on the sample for the sample. Okay. And is also a random variable. Okay. Confidence interval, I told you, it gets narrower with number of observations and it also scales with standard deviation. Okay. What can we say in words about the confidence interval? I would put that as, okay, I'll write it here. Confidence interval is the range of values centered on the sample mean in which the true value may be found with a certain probability. What is that statement? Can we understand that? Let's go back to this table here. Okay, we'll pick any one sample collected by one of the groups. The sample mean is 66.28 and the standard deviation is like 2.28. Okay. The true value, which we got by compiling all the values, is 68.97. So if you just roughly do, like, I'll take one standard deviation from the mean. How much is that? How much is one standard deviation plus this? And how much is one standard deviation to the other side, like mu plus sigma and mu minus sigma? Does this range contain the true value? Kind of does, right? Kind of does. But do you think this will always be the case, even if you make the samples very small? Let's say, for example, I pick two of the tallest people in this room and call them a sample. Would that average be falling, or would that average be containing the true value? Probably not, right? So there is always a finite chance that the true value will lie in this mu plus sigma and mu minus sigma or not. There's a finite chance, right? So how do we write this in a more quantitative way? Instead of going over all the math, what I'm going to do here is to write out a formula for CI, the confidence interval. Oops, sorry. The confidence interval is equal to a quantity which we'll call the t statistic multiplied by the standard deviation sigma divided by square root divided by square root of the number of observations or number of trials. And this t parameter is evaluated at a certain probability and for a certain number of observations. And when we say this is the confidence interval, here's what we are exactly doing. We have an expression that scales with sigma that gets better with number of observations. Like even if you don't fully understand t at this point, what happens when you make 1,000 observations? What happens? You'll have square root of 1,000 in the bottom, and that will naturally make Ci go to 0 as n becomes large. Okay. So the first property that you can easily write down is, oops. So Ci goes to 0 as n becomes large, as we do more observations. Can you tell me what's the interpretation of that? What does Ci goes to 0 mean? Based on the definition, if Ci is 0, what does it tell you about the sample mean? Yes. We have more confidence, meaning the range around the sample mean is narrower and is likely to contain the true value. It converges to almost a point which gets you closer to the truth, ever so closer. Okay, so this is where it comes from, that we keep saying do more observations because it increases the confidence on your mean. Okay, all right. So if I draw this, like a line, okay, I draw as a line. Let's say this is my sample mean, x bar, okay, and the confidence interval is x bar plus Ci and x bar minus Ci. The interpretation is the interval from x bar minus Ci to x bar plus Ci contains the true value with a certain probability. That statement contains the true value with a certain probability. That is taken care by this p parameter about which I'll talk. Okay. I want to take a picture. Okay. So I told you that the sample mean and sample standard deviation themselves follow distributions, and those distributions are called the students t distribution, but we are skipping a lot of the details. Okay, why? Because that'll take like 3 or 4 lectures, which I don't have, and we don't need the intermediate steps. We just need the final expression for the confidence interval. Let me show you a table here. This table is also posted on your Canvas. Okay. So this is the appendix table. Okay. I want you to go to page A3, the third table, where the first table was our standard normal distribution. I want you to go to table A3. Okay. It's all very mechanical in the sense I'm going to tell you how to use the table, not much of theory. Okay. So then if you look here, this n stands for number of observations. If you did, what was the sample sizes? It varied between 4 to 7, right? This n is that 4 to 7, whatever your sample size was, of your group was. For n equals 1, 2, 3, 4, we have 5 columns in which we say alpha of different values from 0.1 to 0.005. This alpha, okay, this alpha where is alpha? Alpha is defined as 1 minus p, where p is the desired confidence level. Desired confidence level. Desired confidence level, meaning if my confidence level is, let's say, 90%, 1 minus 0.9 would be alpha of 0.1, and I would look in the first column. Okay. So what that means is, if we want to compute or if we want to read out alpha for n observations and 90% confidence, 90% confidence, we would go alpha in the first table of n and p equals 0.9. This would be 1 minus 0.9 or 0.10. So you would read this from the first column. Now, if I want 95% confidence, I would read it from the second column where alpha is 0.05. And if I want 99% confidence, I would read it from the third column. Well, that's nothing. That's just me saying where to look. But look at the trend here. If I took a sample mean, let's say we go here, okay, and for the first group, let's compute standard deviation divided by square root of the number of observations, which is 6. Okay, and then I have to enter a t value. Okay, I just took standard deviation 3.87 divided by square root of 6. Okay, if I wanted 90% confidence, what would I do? I would go here, pick up the first value or first column and take 1.44. With me so far, even if it's not fully clear why, but at least you're following what I'm saying, right? I would pick 1.44. 1.44. I'm going to go back here and multiply by 1.440. So this confidence interval I'm going to round it off to 3 decimal points. I'm computing with 90%. Okay, if I wanted 90% confidence, I'm getting 2.275. If I want 95%, what would I do? I would take the same standard deviation divided by square root of the number of samples multiplied by looking at the table. If I wanted 95% confidence, I need to multiply by 1.943. Okay. I don't want to insult your intelligence. I know you're following, but what I'm trying to do is show you that if you take a sample mean and you wanted a lower degree of confidence, the range is narrower. It will look like it's just 2.275 units. If you wanted more confidence, then the range increases. Yes.
Right, so what's the confidence for go to 0.025 at the third one?
So that would be 1 minus 0.025. How much is that? 1 minus 0.025. That's 99. Wait. I used to be good at this. That's 97.5%. Okay, that's 97.5%. You take the last column, 1 minus 0.005, that's 99.5%. Okay.
That means we can't like we can't have an 80% confidence, it's only 90% and above.
Oh, Excel can compute any value that you want. I'm using the table right now to just show you how the trending works. Then you can use the built-in functions to get, if you want 50% confidence, you can evaluate. Yes.
Why do we not always want best confidence we can get?
Best confidence level you get is also equal to more money. If we were just mathematicians, the first part answers itself, but we are engineers. We have to think about money. We have to do project planning and keep the budget under, everything. So look at this line. look at n equals 6. If you want more confidence, this t parameter keeps increasing. Simple trend, right? If you wanted less confidence, you can go further to the back and have alpha equals 0.5. You will have smaller of these values. Okay. So coming back to our statement, if you want a higher degree of confidence, the range increases. If you want a low degree of confidence, the range can be narrow or as narrow as you can make it. Okay. So when you report let's say you are a quality inspection engineer, you try to measure the dimension of a certain component and you have to write a report that I measured 10 samples, here's the mean. And based on this mean, I can't possibly sample all the 20,000 samples that your company makes every day, but you have to write a report that most of our true value of the dimension will lie in a certain range. That is this confidence interval. And what will be the chance? If you let's say you made this calculation with 95% chance, what does that mean? It means 5% of the components can be outside the range, and that was kind of pre-expected. You write that report. Let's say you write a report saying 95% of the values will lie in a certain range. How will they verify that? How would that be verified, do you think? Okay, maybe I should give you a number. Let's complete this and then I'll ask you that question again, okay? Okay, so you have a confidence interval for 90 and 95%. I'm going to write x plus x minus ci, or I'll say mean minus ci and mean plus ci. Mean minus ci will be mean minus ci and mean plus ci. The skill that I'm trying to go for here is for you to understand what is the significance of 63.525 to 68.870. Based on the discussion so far, can you tell me what this range represents? It is a possible range based on the sample that you just collected, in which the true value is likely to be found with 90% confidence. Okay, with 90% confidence. So I'm going to write that in words. This range contains the true value with 90% confidence or probability or chance. Okay. Contains the true value with 90% probability or chance. Now, in this group, now is the moment of truth. In this group, hey, Jonathan, you have that Excel sheet, right?
Yeah.
So you're going to answer this and we are going to check if all this theory holds up. Okay. So we have 63.525 and 68.870. I told you the true value will lie within this range with 90% chance. Okay. You can also interpret that as 90% of the values will lie within this range. So we have the data. We have data on 37 height values, and we can check whether 90% of the data is contained within this range. That makes sense. There are two interpretations of this. First is in a scenario where you don't have access to the original data, you have to take a sample and you have to calculate a mean and then wonder what is the chance that this range x plus ci and x minus ci will contain my true value. This could be that measurement or inspection scenario where you inspect 10 parts, but your company makes 20,000 parts each day. Then you are asking the question, can I take these 10 samples and project forward about what can be expected in the 20,000 parts? Okay. The other interpretation is we have this range, right? The true value is contained in this range with 90% chance. In other words, this range should contain 90% of the values. That can be checked based on the histogram that he's trying to calculate. Okay. So you can do the same for each of these different samples or different groups, the data that we collected. Okay. The data that we collected. Any questions so far? Today have been very awfully quiet. Is there a question? Rashid? Okay. Is it making sense? Kind of.
And if we were to have a whole lined up, read two would be, I'm assuming like every 2 you point out would be, you'd get one person that is in that range.
Repeat that, please.
So you see how you have like 2.275 for the first time?
Yeah.
And what does that mean exactly?
Okay.
Like in practice?
Thank you for asking that. So this, one second. All right. Your question is, what does this 2.275 actually represent? Okay. We understand up to standard deviation, right? Standard deviation is a measure of how much the value spread within a small group or within that sample. Think of confidence interval as a quantity that has the same units as your standard deviation. It's kind of like a scaled standard deviation or a corrected standard deviation. If you look at this formula here, it is proportional to standard deviation. N is just a number, so it doesn't have any unit. And T is also a number that you read from that table I showed you. So Ci and sigma have the same units. It is just a scaled form of the standard deviation. So it's like saying you took the standard deviation and you corrected for two things. One is the size of the sample. The other is the possible statistical variations of the standard deviation itself based on an underlying distribution. Okay. So if you look at this, this line here, the cartoon up here, you have the sample mean and you draw an interval which is x minus ci and x plus ci. This range from x minus ci to x plus ci is what I call the confidence interval. Meaning you have confidence that your true value lies in that interval with a certain chance, not like 100%, but 90, 99 or whatever percent. Okay. The main thing you have to understand intuitively is if you want more confidence, your range keeps getting elongated. If you want 99.5% confidence, you have to multiply by 3.7 as opposed to 1.4. That's nearly more than 2 times. The range is 2 times wider if you wanted more confidence. You want to go from 90% to 99.5%. That last 9.5% is making you double the size of the interval. Okay, we'll do numerical problems, but the main idea is more confidence means you have to accept a wider confidence interval where the true value can be found. The alternate interpretation is take this sample mean. In our case, what is the unit for the sample mean? Inches, right? Inches. That's the height which we entered everything. So 65.8 is the sample mean, and the interval varies from 63.5 to 68.1. And we are saying this will contain 90% of the height values in this population, in this village, in this class. Okay. If I wanted 95%, what will be that range? I'll have to first write CI 95%. Okay, CI 95%, which will be, how do you compute it? Can you tell me now? You just looked at the formula, right? What's the formula for CI? So we'll start with sigma. Sigma divide by square root of the sample size, which is 6, times the t statistic. So how will you read out the t statistic for 95% confidence? 1.943. 6 samples, 1.943. Okay. So we'll do 1.943. 1.943. This is 3.07. I want you to pay attention to the shaded cells here between 3.07 and 2.275. What's the ratio between these two? This is 3, this is 2.2. Right there, it's about what? 3 divided by 2.23. That's about 1.3. The ratio between 3.07 and 2.2 is about 1.3, or off the bat, it's 30% wider. 1.31 means what? It's 31% wider, or nearly 1.32, 32% wider. Okay, so that is like saying, I'll take the sample mean and say X minus CI and X plus CI, okay, X minus CI and X plus CI, mean minus CI and mean plus CI. What is my confidence level? 95%. So between 62 point, between 62.73 and 68.87, I'm saying 95% of the values would lie. It's actually a little low to me. Are there only people who are about only 68 inches tall? I see a lot of tall people here. Maybe you guys didn't write your real height.
Like I said, we got legitimately the same height.
Okay, that was a joke. Okay, I mean, I see a lot of tall people, but I'm surprised that the average was actually only 68. Anyway, okay. So we can check. What we are going to do is, I'm going to ask Jonathan to provide me the original data of all the height values we collected, and you are going to check whether 90% or 95% of the data actually lies within this interval. When you see it, that it does lie, it'll kind of click. That's my hope. Okay. Yes.
So I can see that you're working with the first sample size. The
Right.
first group. So
Yes.
does it work for each of the group?
It works for every group. That is the way. See, that is the whole point. That is, when you think of a group or a sample, okay, each group has its different sample sizes, and depending on who is in the group, the variance and sample mean will also be random. That's why they themselves are random variables. The confidence interval is sort of like a uniform or a normalization metric, which accounts for one, the variability in the data, which is the standard deviation, the sample size, which is the square root of n factor, and the possibility that these mean and standard deviation themselves are random variables. That's why we multiply by the t statistic. So it kind of corrects for all the idiosyncrasies of different samples. Okay. So if you compute the confidence interval for every sample, the data that I have here, every time that interval should contain 90 or 95 or whatever percentage of the data based on the original or the raw data. That is the implication. Okay. So you are going to try that. That is, I'm going to put this Excel file and paste the raw data that Jonathan is going to provide me, and you are going to verify this at home as a homework. Okay, so that you will actually understand what is confidence interval. Okay. One more observation. Okay, look here. What happens? You tell me, look here and tell me. You can focus on any one column. You don't have to look at all 5 columns. Look at any value of alpha and tell me what happens as n gets larger. Sorry? As n gets larger, look at, let's be specific. Let's talk about alpha equals 0.05. Let's look at this column. Just sweep your eye from top to bottom and tell me what happens to the values. They seem to flatline, right? They were initially 6.3 and now they are kind of heading towards 1.7, and then only in the second decimal point something is changing, right? They're kind of flatlining, like converging, right? And if you keep going here, okay, you have 1.645. It kind of goes there. Look at the jump here. From 29 to infinity, it goes from 1.699 to 1.645. What they are practically telling you is above 30, this thing basically remains constant, number one. And I did tell you a few, maybe in the first few lectures, that 30 is the line between small and large. Like 29 means something, but 30 and infinity are practically the same. Okay, this is where that intuition comes from. Look at this number. Or look at all of these numbers. 1.96. Okay. 1.96. Just remember that number. Remember that number. And go up here. This is alpha equals 0.025. Okay. There is a connection between this t distribution and the normal distribution that we learned. And you are going to uncover that connection for me now. 1.96. Okay. What is the significance of 1.96 in the standard normal distribution? Can somebody stare at the standard normal distribution and tell me what's the significance? So if I take 1.96, 1.96, okay? So 1.9 and 1.96, I get 0.975. Can you intuit the connection between 1.96, 0.975, and the table that we just saw back there, which is for alpha equals 0.025, at infinity, we get 1.96. So the same two numbers appear in two tables. What's the connection? That column is for 97.5% confidence. Okay. So if you want to be 97.5% confidence, and if you have a large sample, you multiply by 1.96. That's your t parameter. If you go back to standard normal distribution, 1.96 is the value that you, to the left of which lies 97.5% of the probabilities. Ergo, your inference would be okay. So this is a good moment for you to take 2 minutes, write that down, put your name on it, and submit that as participation exercise. Okay, if you want paper, I'll provide. Just take one and pass. Take one and pass. Question is, the value 1.96. Okay, I'll write it down. Okay. value 1.96 is the value of Z, to the left of which 97.5% of the probability or area under the normal standard normal distribution curve lies. 1.96 is also the value of the t parameter when n goes to infinity. What can you connect from these two pieces of information? Write whatever you can think of. Don't worry about being right. Write, put down your name, and we'll collect it at the end. If you want paper, I can provide. Think and write down whatever you can think of. Infinity and alpha equals 0.025, or to recall, alpha is 1 minus probability or confidence level. So we have alpha equals 0.025 implies P equals 0.975 or 97.5% probability. So I've given you all the information that can be read from the tables. I want you to tell me what you can connect from these two dots. You can talk or talk to me, not you. You can tell me what you think. Yeah.
Table, the 97% chance, or probability.
That the random variable will assume, or yeah, sure.
Yeah. Technically, saying that you're saying the same thing, right? Saying that 97.5% is like they're both the probability, both cases.
In both cases, the probability value is the same. That is, to the left of 1.96 lies 97.5% of the values. In the second table, we say if you made an infinite or a large number of observations, the correction factor is 1.96 if you want 97.5% confidence, or if the interval has to contain 97.5% of your values. Okay, so the inference from that would be, okay, I'll give you one more clue. Okay, instead of me telling you, look at the last entry here. Look at the last entry in all of these. 1.282, 1.645, 2.326, 2.576. Just check up what is the probability value for each of these under the normal distribution table. If you have that normal distribution in front of you, look up just like you looked up 1.96. look up 1.645 or 2.326 and see what you find there. So I'll leave the table here. Okay. It's hard for me to keep going back and forth, but let's see here. What was the second value? Anyone have the?
6.4.
Yeah, look up 1.645. Tell me what you find. Here is 1.6. Here is 1.64, that is 0.9495. And 1.65 is 0.9505, which means the midpoint would be 0.9500. 1.645 would be between 9495 and 9505, or would be 0.95. 1.645 goes to 0.95, and that is the significance level over here. So this alpha matches with the last entry with the normal distribution. Look up for 0.01, that is for alpha equals 0.01. At the last entry, you have 2.326. Look up what is 2.326. And before you look up, anybody wants to guess what the answer would be? 0.01? 99%. Right. If you say 0.01, that's like saying 99% probability. And now if you go back and look, 99% probability is to the left of which number? Is to the left of 2 point. It's between 2.32 and 2.33. So we'll take it 2.325. Okay. You draw the line at 2.325, 99% of the values are to the left of that line. Yes, no? Yes. So now what is your inference? I gave you all the clues that I had. When the sample size is infinity, these two tables seem to be saying the same thing. So see this if you okay, one more clue that if you see it as a clue, this table, the T table and the normal table agree only when this sample size is infinity. When sample size is not infinity, let's say the sample size is like 10, they don't agree with each other. You can check that if the sample size is 10 and you wanted to look for the number that to the left of which is 99% or 95% of the values, that is not 2.764. You can check that. What is 2.764 in the normal table? In the normal table, 2.764 is 2.764 is 0.997. Okay, 0.997. All right, 0.997. If you convert 0.997 into an alpha value, what would that be? What is 1 minus 0.997? 0.03, whereas this is 0.01. It's not exactly matching when the sample size is finite, but it seems to line up exactly when the sample size is very large or infinite. Yes.
So are you emphasizing that it's important to have like 30 samples? Like, are you?
At least 30. I mean, without knowing the context, I would be at risk to say just 30 blindly. But if you can, 30 is a good number to have. It depends on the experiment. Like if you want to go in and measure a few voltages, it costs nothing to do that. But let's say you do a very complex medical experiment with 30 animals. Each animal costs $40,000. So I can't blindly say 30 for everything. The budget may not permit that. So it's contextual, but if wherever possible, 30 is a good number to attain or aim for. Okay. I have to put a lot of caveats in that.
30, assume that it would be.
Thank you. that's what you need to put on your sheet. If you reach 30 or more, you can describe your statistics pretty much using normal distribution. Whereas 30 or less, you would be using the t distribution to describe your statistics. So here is what you would put if I were you. For n greater than 30, we would describe probabilities using normal distribution. And for n less than 30 generally, we would describe probabilities using the student's t distribution. I mean, when you look at the normal distribution table, there is no mention about n. It's automatically assumed n is infinity there. Whereas in the student's distribution, there is a dependence on both n as well as the probability level, which is what you see as two columns. Like you see a column for n and a row for the confidence level or the probability. So it depends on both n and alpha. That's the idea. Okay. So there is only going to be one type of problem asked about confidence interval in my exams, which is you are given a mean and standard deviation for a small sample. You need to estimate the confidence interval. This is the only type of problem we will do. But the key statement is what you will write at the end. Okay. So I'll write it down for you. Then we'll start with some examples. Step 1 would be compute sample mean and standard deviation. Okay. The formulas we would use are these. And you're going to do this with calculator in the exam. There is no Excel on the exam. So you would do this manually. Okay. Or these may be provided. It'll just skip ahead to the next step. Okay. These may be provided. Then the second step is compute confidence interval. Okay. And how you do that is using this formula. Compute confidence interval using this formula. Okay. This requires reading the t value from the appendix or from A3, where alpha, the parameter that appears in the table, equals 1 minus p. And p is the confidence level. Okay. These are the easy parts. The third step is writing a report. I mean, writing the true value, something like this. The true value of the quantity that we are seeking lies in the interval we'll call the sample mean as x bar. Okay. X bar plus minus ci. X bar plus minus ci with 3% confidence. You should state this specifically. If you just get a sample mean, that is not the true value. If you just get the confidence interval, that by itself doesn't mean anything. If you get the interval x plus or minus ci, that's the interval in which the true value may be found with this p% confidence. Whether you are dealing a cast iron skillet for the kitchen or you are dealing a space shuttle that goes to Mars, the confidence level matters. Why? For the first application, you can have a tolerancing like 50%. It doesn't matter. It's a very low, it's a high tolerance. Oh, sorry. It's a very crude application. But if you are sending a space flight And if you make an error of a certain percentage over millions of miles, that error is going to amplify quickly. So there you need more confidence. So this statement has to be complete. It has to have the true value. It has to have the interval and the confidence level. This is what I really expect you to learn from this exercise. Okay. And we'll try to do examples in this template. Okay. Any question before we move on to we have some time for an example. So for next class, the homework for you is take the raw data that we provide. Okay. For your convenience, turn it into a histogram. Okay. Compute the confidence interval for each group or sample that we generated. Okay. And check if at a certain confidence level, let's say 90%, if 90% of the data lies in the calculated range. You're going to look at your histogram and try to verify whether 90 or 95% of the data lies in a certain interval. Okay. So what I will do is I will delete some portions of this and let you do the calculation again and essentially post this template, and you can start from here and do your work. Okay. Questions for me? Yes.
Well, after that, I'm question about your index on the table.
Okay, after he finishes. So you do this at home, bring your answers, and I'll do some prompting next lecture, meaning I'll ask some questions and you'll write the answer to those questions based on your calculations, and that becomes participation exercise. One more 1% score. Yes.
So you can do the cost as 90 or
You can choose 90 or 95. What you have to verify is if you choose 90%, does 90% of the data actually fall in that range? That you are going to check. Data will be the original data of all the height values will be provided to everyone. I'll upload that. Okay. Yeah, you had a question.
Yeah, so like you said that N is the sample size, right? Like the number of, so why did it be why is like you know there are 9.925 and the row 2, why is the number lower on like row 19 if it's more samples? Wouldn't that like not for that more confident?
I don't understand your question. Can you repeat?
So like I just don't understand why it's going from 9 to 2 if there's more samples involved.
9 to 2.
Like 9.925.
Yes, 9.925 to 2.8.
Yeah, if there's more samples involved.
So it is decreasing. You agree with that, right? If you look at, see, let's say you are designing a rover for Mars application and you want a certain component with a high degree of confidence, you will have, let's say you selected 0.995 or 99.5% confidence, you will multiply by this number. Okay. If you wanted a lower degree of confidence for a low stakes application, you would select something with 90% confidence. It still decreases from here to here, but relative to these two, this is a larger range than this. That's what I'm saying. If you wanted more confidence, your range will get longer. The other way of saying that is, if you want to encompass a larger fraction of your data, obviously your interval will be wider. I can blindly say that every 100% of the data in this room will lie between 5 and 7 feet. It's most likely to be true, right? I don't have to do much math for that. But if I want to say very precisely between 5.4 and 5.8, how much data will lie? and I don't get to sample all of you. I have to talk to 5 people and I have to make an inference based on 5. That is the skill and art. If you had access to all the data all the time, there is no need for any statistics. The whole field exists because you cannot have access to all the data all the time. Okay? Yes.
Want to balance it so that your CI value is as small as possible, but the percentages is optimal.
Yes, very nicely said. You want higher confidence while you are able to get a narrower range, which you have one control variable, which is the number of samples. Number of samples, if you are able to increase, you can get higher confidence and narrower range. But that ties back to cost and time and practicality. Very nicely said. Yes. Okay, so yeah.
Said before. Actually, you don't.
I don't know anything about the population. So let's say you 5 of you are my sample. I can talk to you and get your data from you. I have to use that data to project it for the entire class, whom I can't meet in total. That is the part where I said I can't know the entire values. I have to go by a sample and project it forward. I do know my sample. You are all going to do it for all the groups. That is, it's just a practice exercise. You just do it 5 or 6 times to learn, and each group has a slightly different mean and different confidence interval. So you can first learn about how to do the confidence interval calculation 5 or 6 times. Wouldn't hurt to practice. Then for each interval, you look at the histogram and see whether 90% of the data or 95% of the data falls in that range. It's a yes or no question at the end. Look at this question here. Check if at a certain confidence level, if 90% of the data lies in the calculated range. The answer to this is not a number, it's a yes or no. Either it falls or it does not. So you have to write, it's a yes or no question. Okay. Just getting you to exercise these muscles, that's all. Okay. All right. Any other question? Yes. Yeah. 3% is the confidence level. If I want 90%, P is 0.9. If I want 98%, P is 0.98, and so on.
So B is probability.
See, probability, confidence level, chance, odds, these are all synonyms. They all have the same connotation. Next questions. Okay. I don't want to start an example now. I'm going to format this Excel file and post it, and we'll start with a few examples next lecture. There is just one more topic in this statistics module. It is called hypothesis testing, which is what you need for your projects. That is, your project has to, in the 5 minutes, let me talk a little bit about your project. If you can hold your packing, please. So the project that you will choose, first of all, start forming groups and email us your group members, 3 or 4 students per group. It has to have a hypothesis. Anybody know what a hypothesis is? It's a theory or a question that can be answered and tested. Like, for example, Ranga is crazy. That's a hypothesis. And I have to come up with an experiment that will either prove or disprove that theory. Okay. So that was just a joke. But if you are doing a project, let's say it is some kind of a measurement, you need to have an equation that predicts what the quantity you are measuring is. And then you have a measurement, then you are going to test that equation or theory. So it has to have a hypothesis. We have to learn how to do hypothesis testing, and then you are going to do data collection, use the data to test, which means accept or reject the hypothesis. That's the whole project. You can select your own project if it is hypothesis based. If you are unable to select, I will help you select, or I might assign a project that's common for everyone, and you are welcome to pick that. It's not about each one has to do something different. It's about how you learn hypothesis testing. It can be computational, it can be experimental. That is, your data generation can be computational or experimental, but it still has to test some hypothesis. Okay. So next lecture, I hope to discuss some examples and hypothesis testing. And hopefully by next Thursday, I should wrap up statistics. And I'm asking you this, how long do you think you need to come up with a project idea and write like a 1-paragraph synopsis to give me?
I think give us what you would assign as like a standardized, so that way we have a good idea of what you're expecting.
So by next Thursday, I'll have my standardized project and I'll give you exactly 1 more week. By 26th, I need everybody to have formed a group and selected a project. If you don't have a project on 26th, just to scare people, I'm going to dock points. And what formula I'll use to dock points, I'll also think about that. But I need this done by 26th. Okay. One more thing I wanted to run by you guys. Since I started doing these participation exercises, I got some positive feedback that some of you like this better. Again, it's sample. I don't talk to all of you. So it's again sampling. But my sampling tells me that this is landing better than just doing example problems. So I'm thinking about taking some weightage out of the comprehensive final and doing more participation scores. That way, instead of that being 20%, maybe that will become 15% and you get 5 more participation scores. You have to show up, you have to talk, you have to write something and give it back to us. Easy deal, right?
Yes.
So everybody is okay with that? If I reduce weightage on the final and all right, good. So please, that requires your cooperation. Bring your laptops every day and we'll do this from most lectures from now onwards. Okay. Thank you.
So in the example of the height, we value don't get it, right?